Hello everyone. Today we are going to talk about production of X-ray. In this lecture we are going to go through ionizing radiation and what is atom. Then we are going to discuss briefly the types of ionizing radiation and the main components for X-ray tube. Radiation is any energy that comes from a source and travels through space, such as light. Ionizing has sufficient energy to dislodge orbital electrons and ionize matter, X-rays, gamma rays, and neutrons. Non-ionizing does not have sufficient energy to dislodge orbital electrons and cannot ionize matter, electromagnetic radiation with energy below the far ultraviolet region, e.g. visible light, infrared, and radio frequency. Historically, X-ray was discovered by Wilhelm Röntgen in 1895 when he was working with cathode ray. He discovered that this radiation could go through the tissue human. One of his famous experiments was a film of the hand of his wife. To talk about ionizing radiation, first we need to go into more detail about the atom. So, what is the atom? The atom is the fundamental unit of the matter. Simply it consists of a central nucleus containing mostly charged proton and neutral neutrons, surrounded by cloud of negatively charged electrons. The interaction between these particles determines the properties and behavior of the chemical elements. Types of ionizing radiation. The most common types of ionizing radiation are 1. Alpha radiation. Alpha particle is simply the nucleus of helium. It consists of 2 protons and 2 neutrons. Because of their charge and large mass, alpha particles are easily absorbed by materials, and they can travel only a few centimeters in air. 2. Beta radiation. Beta particles are high-energy, high-speed electrons or positrons that are ejected from the nucleus by some radionuclides during a form of radioactive decay called beta decay. Because its mass is lighter than alpha particles, it can travel more distance in the air compared to alpha particles and needs thicker material to absorb it. 3. Gamma radiation and X-ray. Gamma radiation and X-ray are the most common types of ionizing radiation that are used in radiotherapy. Because gamma rays have no mass or charge, it can travel much farther through air than alpha or beta particles. X-ray like gamma ray, the only difference is the origin, where X-ray is generated from the electron cloud while gamma ray is generated from the nucleus. The X-ray tube consists of a cathode filament and anode target sealed in an evacuated glass envelope. The target must have a high atomic number and high melting point, like tungsten, where its atomic number equals 74 and has a melting point of 3370 degrees Celsius. When the cathode filament, which is negative electrode made of tungsten, is heated up, it starts to emit electrons. The emitted electrons are focused into a narrow beam by a focusing cup in the cathode. This focused electron beam is then directed towards the anode, which is the positive electrode. The concentrated and high-speed beam are accelerated across the vacuum in the tube towards the positively charged anode. This acceleration creates a kinetic energy sufficient to generate X-rays. Rotating anodes is used in diagnostic X-rays to reduce the temperature of the target at any one spot. Focal spot, the anode or target area from which the X-rays are emitted. In diagnostic tubes, it is important to have small focal spot to produce sharp radiographic images. For therapeutic, large focal spot is accepted because the image quality is not a concern. The primary method of X-ray production is through Bremsstrahlung, which translates to breaking radiation in German. When the high-speed electrons approach the positively charged anode, they are decelerated or slowed down due to the strong electrostatic forces and X-ray is produced. These figures show how X-ray is generated when the electron approaches the nucleus and deflected, generating X-ray. In addition to the Bremsstrahlung X-ray, there is characteristic X-ray. Characteristic X-ray, when incident photon or electron interacts with an inner electron in the target atom and eject it, the empty location of ejected electron is filled by another electron from higher atomic shell or orbit. The difference in energy between the two shells is emitted as X-ray. The ejected electron will travel with energy equals to the energy of incident photon or electron minus the binding energy of its shell, while the emitted X-ray will have energy equal to the energy difference between the two shells. It called characteristic X-ray because it is characteristic of the atoms in the target and of the shells between which the transitions took place. Unlike Bremsstrahlung X-ray, the characteristic X-rays are emitted at discrete energies. So, the overall produced X-ray photons from the X-ray tube are in form of heterogeneous spectrum. This spectrum consists of the continuous Bremsstrahlung X-ray superimposed by the characteristics X-rays. Heal effect: X-rays are produced at various depths in the target. For X-rays produced from greater target depth, the attenuation will be higher than the X-rays produced from near surface of the target. Consequently, the intensity of the X-ray beam decreases from the cathode to the anode direction of the beam. This variation across the X-ray beam is called the Heal effect. This effect is pronounced in the diagnostic tubes due to low X-ray energy and steep target angle. The Heal effect can be minimized by using a compensating filter. Because the emitted X-ray has a spectrum of energies up to the maximum applied voltage in the tube, it is hard to characterize the emitted X-rays in terms of energy. Although the average X-ray energy is approximately 1/3 of the maximum energy, it still cannot be used to describe the produced X-ray energy, especially due to filters, as filtration significantly alters the average energy. Half-value layer is a common term to be used to describe the beam quality, especially in the diagnostic beams. For therapeutic beams, the TPR 20/10 is one of terms that can be used to describe the beam quality. The X-rays generated are emitted in all directions, but a collimator or beam shaping device is used to restrict the X-ray beam to the desired area of the patient. Tube efficiency: the tube efficiency is the ratio of output energy emitted as X-rays to the input energy deposited by electrons. The efficiency depends on the target atomic number and the tube applied voltage. For example, for tube with 100 kV, the efficiency is less than 1%, while the 99% of the input energy appears as heat. The efficiency improves for high energy X-rays and can be 30% to 95% for accelerator beams. The produced X-ray beam then passes through the patient's body being examined or treated. Different tissues or materials attenuate via absorbing and scattering X-rays to varying degrees, creating variations in the transmitted X-rays. The photon and electron interactions with matter will be discussed in more details in different lecture. For diagnostic purposes, the X-rays that pass through the patient strike a detector, like an image receptor or digital sensor. The detector converts the X-rays into an electrical signal, which is further processed to create a visual representation of the internal structures, known as an X-ray image or radiograph. Below examples for general X-ray and CT images. The produced X-ray can be used for treatment purposes as well. The X-rays used for treatment purposes has higher energy than those used for imaging purposes. Thank you.